Well, we're back at the Cave of Science, and we're going to look at light, which is part of the electromagnetic spectrum. The electromagnetic spectrum, all these waves are composed of two fields, an electric field and a magnetic field. The beauty of the EM spectrum, and I'm just going to keep referring to it as the EM spectrum, is that the EM spectrum, electromagnetic spectrum, can go through a vacuum. So the EM can move through space or move through nothingness. If you remember, the sound wave or longitudinal wave has to have a medium. The electromagnetic spectrum does not. Think of light from the sun. And we're going to look at the sample of the electromagnetic spectrum here and kind of point out some things. And let's see if I can get it running right here. The electromagnetic spectrum, we got a picture of it right here. And you can see up here we have the different names for parts of it. Radio, microwave, infrared, visible, UV rays, X-rays, and gamma rays. In this line right here we have a wavelength from very, very long to like 10 to the minus 9th, 10 to the minus 15th to very, very small. In the third one, which is right here, we have frequency. I should put this right here. We have wavelength. This line is frequency. And again, frequency is the number of crests that pass a given point per second. And you can see as frequency increases as you go from the radio end of the things to the gamma rays. Also, the higher frequency, and we should write this, the greater the frequency, the greater the energy. If you think about it, you're constantly getting bombarded with radio waves. You're getting bombarded with microwaves. We see visible light. Visible light kind of sitting right here. You go to the dentist to get an x-ray, they put a vest over you because you don't want to be exposed to x-rays. Gamma radiation from a nuclear bomb, it would kill you. So when you start getting these very, very, very high frequencies, what you end up having is more and more energy. Notice this right here. When you have low frequencies, you have large wavelengths. So remember that relationship. The lower the frequency, the longer the wavelength. And here's kind of a graphical representation here. On the opposite end, the higher the frequency, the shorter the wavelength. And this really relates. You have high energy out here, and these on this side are lower energy. And they kind of give you some examples here of the size of the wavelength, if you will. When we talk about light, we're really talking about this area right here. Light's pretty small. It's a pretty small area. As you can see, this is all we see right here. This is it. And it's a very, very small area. Real quick, light is an EM wave. Light is an EM wave, and the unique thing about light, it has properties of a wave and particles. When you get into physics, you're going to get into this whole wave particle nature of light. But an interesting thing on an electromagnetic wave or a light wave is a term called a photon. I always remember this. You go back to the old Star Trek, the old photon torpedoes, but a photon is a packet of EM energy. It's a packet of electromagnetic energy. Quite often they'll talk about the dual nature of a light wave or electromagnetic wave. When they talk about this dual nature, they're talking about it has properties of a wave and it has properties of a particle. Remember, a light wave also is a transverse wave. Light is transverse. That's where the particles move perpendicular to the direction of motion, and you're going to see light quite often represented in these terms, or any electromagnetic wave. So that's kind of the beauty of electromagnetic waves, is they can travel through anything. On the next video, we're going to look at a little bit on the reflection of light off some smooth surfaces.